Hello, welcome back. Today we're going to be taking a look at solving differential equations through a technique that we call separation of variables. This note today will look very familiar to us. We're going to combine a lot of what we've talked about in the past. To start off, let's review what a slope field is. Now, you might remember we had this vector map in our previous video dealing with slope fields. And we call it a vector map because we have arrows, where a slope field does not have the arrows. And we said, well, if we place a leaf on the panhandle of Oklahoma, and we want to find out, well, where will it wind up at? So we were able to use our arrows on a vector field to kind of predict about where this will end up. And it looks like somewhere out in South Carolina before it enters into the Atlantic Ocean. And this is what we call a slope field. Now, a slope field is very good at predicting where we will wind up with. But what if we're not given a graph or given a slope field? Well, to solve something that if we don't have a graph or a slope field, we have to go back to a differential equation. And we talked about this earlier this year. Earlier this year, you might recall, we solved equations in the form of dy dx is f prime of x. We'll see an example like this in a few minutes just to remind us, where the derivative is in terms of x. And we might have seen like this, dy dx equals, let's say, x. And we said to solve it, we would multiply both sides by dx and we would integrate. Y would become x squared over 2 plus your constant of integration. Today, what we're going to be looking at is solving a differential equation where the derivative is in terms of both x and y. And if you're thinking this sounds kind of like an implicit, you're not too far off from the actual of what we're actually going to be doing today. To solve something like this, we use a technique that we call separable differential equations. A differential equation can be used to show the path of a function. For example, we can use the map above. That is our leaf. If we take a look above our leaf, we can kind of predict where it's going to go. This slope field is a map, is a rendering of our slope field, and it can be used to predict a path of a function. So if we're not given one, we have to do a little more calculus. So imagine that given the velocity of an object is modeled by this equation right here, ds dt is 2 over s. Notice this is a velocity, it's my change in position over my change in time. Now, thanks to Newton and his calculus, we can find the equation that represents position. We've talked about that before. If we have position, velocity, acceleration, going down, we're taking a derivative, and going up, we're going to take an antiderivative. So I need to integrate this. So I'm going to rewrite it. ds dt is equal to 2 over s. Well, the first thing I'm going to do is I want to what's called separate my variables. Notice this s right here. You see this s? I need to bring it over. So to do that, I am just going to cross multiply. That's going to give me this s ds dt equals 2. But if you notice, we still have this dt on the bottom. I only want the s's over here, so I'm going to multiply both sides by dt, and I would get s ds equals 2 dt. And now comes the calculus part. I am now going to integrate these sides. If I integrate the s, and I'm going to integrate the 2. Now, when we integrate the s, it's with respect to s right there. So that's easy. That's just going to give me s squared over 2 equals, I know what you're thinking, you're forgetting your plus c. Hold on a minute. And now I'm going to integrate this 2, but the 2 I'm integrating with respect to t. This is why we call it separation of variables, because I got my s's on one side and anything else and t's to the other side, to the right side in this case. So when I integrate here, I'm going to get 2t plus c1. And this is where our constants come into play. Because I'm going to have a constant on the right side and on the left side, I only need to put the 1. So solving it, I am now going to solve for s. Solving for s, we would get s squared equals 4t plus 2c1. Now, I can let this just be c2. And the reason I can do that is if I take any constant and I multiply it by another constant, I'm just going to get a new constant right here. So we now have s squared equals 4t plus c2. Just a nicer way to write it. Therefore, solving for s, be careful. We're going to get two answers because we're taking a square root. So we get plus or minus the square root of 4t plus c2. And this is what we call a general solution. We call it a general solution because we have that plus c right here, and that plus c tells us that this is not unique, so it's just a general solution. And that's what we're saying here below. Note, we still have that plus c. This, of course, means our answer is not unique. But what if, whoops, can't spell today, what if we were given the initial condition 0, 4? Well, now they're saying if t equals 0 and s equals 4, I can now solve for c2. And that's easy to do. If I just plug them in, I get 4 equals plus or minus, excuse me, square root of 4 times 0 plus c2. Now we are in kind of luck here. Notice my value here is positive. That's a positive value. So which means of my plus or minus right here, I only want the one that's positive. So this is the one I'm going to use. So I could write this as 4 equals the square root of 0 plus c2, or c2 just equals 16. So my final answer, if I plug in s equals, excuse me, positive. Remember, we only wanted the positive, so I don't need the plus or minus. The positive square root of 4t plus 16. And now this is unique. This is akin, if we look at the map of Oklahoma, right? I have all these vector fields, right? All these slope fields. I have a lot of different places going in different directions, but only one goes through the panhandle and gets me out of this point in South Carolina. And that's what kind of what down here says. Just like the map above, by placing the leaf of Oklahoma, we can predict the path, the exact path of this particular leaf. We sometimes call this finding the particular solution, and that's what we call this. This is called a particular solution. All right, goes to video number 2. We're going to take a look at a bunch more examples. I'll see you then. Bye-bye.